This is yellow.
Fixed?
Yes.
Yep.
Okay, perfect. So, yeah. For anybody joining on the stream, we talked basically through the points there. So, yeah, I won't repeat all of it. Sorry. And then, yeah, we have those higher level abstractions, and we get things like the timeline, where you can say, I want to send a new event to the timeline, and it's immediately appearing in this reactive stream, and then in the background putting it into the send queue if you don't have network, and then sending the event. And then there's a last crate in this Rust SDK monorepo, and that's the FFI layer. And this is basically just to get Rust compatible with other programming languages, but it actually does a little bit more than one would expect. So it actually has even more abstractions to make it more accessible for actual developers in Kotlin or Swift. And it's using uni-ffi. So basically, the idea is you could just have this one set of instructions, how Rust code is mapped to other programming languages, and then it's just getting, it just generates bindings for all kinds of languages. So as of now, what kind of platform support do we have? So as I said before, we have uni-ffi with Kotlin and Swift. That's why it works with Element X on Android and iOS. But there currently is no support for TypeScript. And as I said, or as the title says, like this talk is all about getting the Rust SDK running with WebAssembly and then building a web client based on the Rust SDK, which, yeah, as of now, didn't really work. Because most of it, uni-ffi, like, doesn't have bindings to TypeScript. And there is parts of the Rust SDK which are already used in Element Web, actually, and that is the crypto crate. So the crypto crate has specific WebAssembly bindings, which are not uni-ffi, because you need to do your own thing, and that is what we use in Element Web, so that parts of Element Web actually already run on the Rust SDK. Cool. So the next thing. So now I just go through like a very rudimentary introduction to WebAssembly. So basically, it's just CPU instructions, as it says, WebAssembly. So there's no such thing. Like if you develop for JavaScript, you have basically the whole browser API, which is almost like an operating system. And in WebAssembly, you really just have executable code without any environments. So you're lacking all the common runtime features. This goes as far as you don't even have access to like system time, because it's really just executing code. And you also don't have any DOM access. So all those additional things you would need through some bind generation to some other programming language which then has native integration with the platform. There is a performance penalty to it. Even though it's pretty performant, it is not compiled for one specific architecture. So the assembly format is relatively generic. Hence, there's a performance penalty. And if you want to have a dependency, since there is no such thing as like a standard library or like a system, system integration, you need to ship all your dependencies inside the WebAssembly blob you ship. But it is super versatile, and it is a compilation target. So multiple programming languages can be used to then build for this compilation target. And just to bring this other word, which probably lots of you already have heard also into perspective. So WASI, which is the WebAssembly system interface, then fixes some of those things. So basically then you cannot just have this like executable environment, but you have a little bit more system interfaces. So you need a slightly more complicated container which can execute WASI. And there they try to standardize specific requests to the outside world. So they start really slow by just making at least something like system time available and defining, okay, a WASI container needs to provide a system time API, and then you could do those kind of things. So it needs a more sophisticated host, knowing about all those, all those specific API calls. And then in the next slide, so this is now the core two things we need if we want to have the Rust SDK run in the web. Like entirely, like up to the UI crate, where we have those like really pretty abstractions. And the one thing is we, of course, first need to get it compiled. And that is not too trivial, because each compilation target in Rust has its own specificness to it. And then the other almost harder challenge is that we then have to do interfaces to the web environment. So we can actually, do something with the web browser with it. And those interfaces exist for the crypto crate, and also the first aspect, compiling, exists for the crypto crate. But if you try to do the full SDK, that doesn't work. And so now we are in the section of compiling the SDK to WebAssembly. And since we do use things like time for generating standard times and so on and so forth, those need to be called in JavaScript. So we need to have like syscalls or like binding calls to JavaScript to then get the time and then use that time in the WebAssembly thing. And then the web also don't has any parallelism. It's concurrent, but you don't have like multiple threads except with web workers. And since Rust is very highly, and the Rust SDK as well, built around like actual parallelism, and there's like lots of send traits and sync traits, and this is all, it should all be trivial in WebAssembly because you don't have this problem if you don't have parallelism, but you still need to get all your code and traits working, and you need a lot of config flags that if it's WebAssembly, you treat it as if it would be send and sync, even though, it's not, but you will never run into parallel situations. So there's just a little bit of work to be done so it compiles properly to WebAssembly. And the cool thing for this is this has happened really recently. There wasn't too much work involved anymore to get it working, because since the work from the crypto crate already was ported a little bit into the main crates, it weren't too many changes. Like time is something I mentioned a lot, and those multi-threading things. And even nicer, Jonas, a former Element employee, got funded by Filament to then also put it on the main branch of the Rust SDK. So basically using the main branch of the Rust SDK also is compatible with compiling it to WebAssembly now, which is super cool, up to the UI layer. And then the second challenge is the interface challenge. So as I said, uni-ffi doesn't support JS and TS. There will be a note later on. So this is like, don't take this as a fact. It's just like what it was a couple weeks ago. So currently the WebAssembly bindgen needs its own implementation. So we have the uni-ffi bindgen, which is already 10K lines of code. And for WebAssembly, would need to do the same thing again. And that is, and then if we do, and that is just for the crypto crate. And then if we would do this for the full SDK, that would be even more work. So basically, building specific WebAssembly bindings for the full UI crate would be insane. And the only way that would make sense is through uni-ffi. And now I talk about different API cuts. So at what point do we actually do the transition from the Rust SDK to the web world? And here's the example we currently do in Element Web. So we have the really big Rust SDK, isn't even used. We have the crypto crate, that is used, and then we have the black box over here, which is then the binding layer to TypeScript. And then we have the JS SDK, and this binding layer to the crypto crate. And this is how we built the whole web app, and TypeScript has a direct interface to the browser, so that just works basically. So this is basically the architecture we have in Element Web. And based on this architecture, I did a couple of more graphs. So those are possible ways one could think of a solution to do a Rust SDK-based matrix client in the browser. So the top one, what I just introduced, what Element Web is doing. Then one could consider just only using the Rust SDK, not the UI abstraction, and do pretty big bindings to a web app, and then build everything in TypeScript without the JS SDK. The next option would be even harder, where you have the crypto crate, the Rust SDK crate, and then on top you have this UI crate abstraction, and then you build really big bindings to then have TypeScript running and the browser. And the last solution would be that you just don't stop using Rust here, but you would then also build your web app in Rust and WebAssembly targets. And then to actually communicate to the browser, you use a sophisticated web framework, which just for its purpose already has all the system calls to the browser. Those are the four examples also listed on the left. And one of those web frameworks one could use is Dioxys. And this is then also basically the example I'm bringing to you today. So this is just like a very short introduction to Dioxys. It's a Rust-based browser front or web front-end library. Here's like a little code snippet from their documentation, which is like their basic example. It's very inspired by React, or at least if you're a React developer, it looks familiar. It's inspired by multiple things. So you have useSignal, which one can think of as useState. And then as soon as we use this signal object in this RSX, which is the equivalent to JSX, we subscribe to the signal. So this block is now subscribed to the state. And whenever that state changes, it just re-renders the specific RSX. And here we change the state, and it's all pretty nice. So in the background, this plus equals operator connects to the or sets the signal and then emits functions, but it's all very beautifully hidden in this access thing. And then, this is based on Tauri. That's something I still wanted to mention. And it already includes all the bindings to then talk directly to the browser. So technically it works that they have their own VDOM, and then based on that VDOM, they just sync the DOM with the browser. And they also have something pretty cool, which I just wanted to note as a side note. It's called Blitz, which then uses their VDOM and directly renders it into their own DOM-like browser, but it's just GL code, so they don't use any like browser dependency. They just use their VDOM and directly render it in like a native OpenGL canvas. Okay, so now we get to the demo, and it seems like I don't even have too much time anymore. But basically, this exact project I did, and it wasn't even that big of a project because the UI layer is doing so many things already. So it was mostly hooking this up with Dioxys, and this is now a Matrix client you will see that is using the Rust SDK in the browser. It's not too obvious that this is a browser because it's like this weird browser, but it is. And then, you can see this is just a basic Matrix browser client. I'm not even sure what I was planning to show here, so definitely sending messages.
You just did it.
Yeah. I'm also not sure why this isn't closing. There we go. So let's say hi. It's like the first example, and it's sending it to the room. Then you can select different messages and then edit them. And there's like the really big advantage of using this timeline abstraction. So if I edit this message, it will update the timeline, and it's all pretty easy to develop, and put it in the send queue and then send it to my other clients or like anybody else in this room. And when I do something in a different client, let's say, this should be like this room over here, and I say test, then I'm also highly benefiting from the reactiveness of Florian said hello world, and we can see that it's immediately updating this one over here. Also in the timeline, because it's all those reactive primitives from the Rust SDK, which is super, super nice. So this is like, it's like a project you would advocate as like a 1 hour project. In reality, it was more like 15 hours or 10 hours. But it's very, very little code. And I wanted to go, I'm hoping this doesn't like entirely break the length of the talk. I wanted to give you like a very short run through in how this code looks like. Not sure what my VS Code is doing here. Is this a problem? You're right. Okay. I was about to reload the window. So basically, I just want to go through a couple of lines of code. So this is interesting, where we set up the timeline events array using a Dioxys signal. And then as the next thing, sorry, this is super awkward to work like this. We have like the main rendering code, the main subscription code. So we use the stream primitive from the Rust SDK, which gives us a vector diff. And then this vector diff just gets applied to the, in this D object, we have the timeline events. It's a little, it's not too easy to read because I gave it such small names. But we take the diff, we apply it to our timeline object. The D object is the diff and the T is the timeline. And then that's basically all the code we need to do. And this is all the setup to connect everything to the Rust SDK. And of course, I didn't even mention that this all does encryption and everything. And then we have this timeline events array. And with this timeline events array, we then just have to do the rendering. So here we are in this RSX object. And the rendering is pretty straightforward. So we just do they are also added a little bit of annoyances because I wanted to know what the last messages is. So I'm doing this peekable iterator, but at the end it's just going through the iterator, mapping the items to this message cell view, which is just a function, not even a Diaxis component. That is just like taking the item object, which is like a super easy to work with message item, and then converting it into HTML. And then the next bit is just going quickly through how we do editing. So we have a button on click, and the on click message then gets connected to this function. And here we again use this like super high level timeline thing and just do timeline.edit and pass in the new message. And the new message we get from composer message, and the this is also a signal. And then we just read whatever is in the composer. And that does all the things, like setting up the correct event, encrypting it, sending it, updating the timeline so we have real-time feedback and immediately see the updated change. So the developer experience is super, super nice with this. So yeah, this setup is what I just demoed. And then there's like this one big elephant in the room, which I also wanted to show you. So basically if we...
Have you seen the console?
I'm trying to. There we go. So if I do a reload here and we type in Wasm, now we can see that this is actually a... Oh, God. No, it is here. Yeah, it's actually a almost 0.5 GB WebAssembly binding. And that is, of course, super embarrassing and kind of annoying. But there are things you can improve this. So the first is you just don't build debug flags, but you actually do a release and do some optimizations on it. So then you're down to 13 megabytes. Which is okay, and then luckily Wasm compresses really well. So if you just do a zip compression on it, you're down to 4 megabytes, which is still not the best. At least we improved it by 100x compared to the debug symbols. But it's definitely like with internet nowadays, it's a reasonable solution and not absolute insanity. And yeah, this is the dev experience. I actually did the order wrong there. So imagine I would have done the walkthrough through the code now. And then there's this other really big news that the uni-ffi ByGen React Native is a project which tries to do uni-ffi, but for React Native, hence for TypeScript. And this makes this also a working solution. So basically, we have now 3 working solutions how you could use the Rust SDK in the web. So this works then that they take the Rust SDK UI, where we already have the really big binding layer for Swift and Kotlin, and they just expose the same binding layer to TypeScript. And then you could also use React or any other web front end based on JavaScript and basically have this kind of architecture, because all this green stuff, which I first said it's like this huge project one would take on if you use Wasm ByGen, you just get for free through uni-ffi. So the key takeaways, do I even have time for the key takeaways? Guess that's fine. So a matrix web client can be built now with the Rust SDK using Diaxis, and maybe in a week, or I'm not even sure what the current publishing state of the uni-ffi is, also with TypeScript and JavaScript. And you get lots of benefits from it. Like, it's a very well-maintained crypto. It has key backup. We have even widget support because of the element call work. Lots of it, at least. Some would still need to be done, and there's actually something I tried to get into this demo. But then I just spent a huge amount of time to getting the crypto feature, the widget feature compiled to WebAssembly. This now worked, but there were still some other issues, so lots of time spent there, which didn't improve the slides, so they still are pretty blank and little colors. But on the other hand, we do have progress on widget support now with Wasm. Still probably takes a week or so, but then this also would be a thing. The event cache is in there, almost. There's no IndexedDB adapter, but that is also something which isn't too hard to do. And you have matrix RTC support. That's actually something I can show real quick, because that's kind of cool. So if we log back in here, and then I take my So matrix RTC doesn't mean that calling works. It just means that it is aware of calls. So if I just go here and then call this guy, like this account, it should say at some point, that there's an ongoing call. So it detects the state and the abstraction we have about reactively showing the call. And then I think we're over, right? It has simplified sliding sync, and soon it's also possible to get all the same features with the uni-ffi engine. Cool. Thanks for listening.